Well, welcome everybody to this Facebook Live broadcast where we are going to explore the intersection between Christianity and science. My name is Dr. Fuz Rana. I'm a biochemist, a Christian apologist, and I'm also the Vice President of Research and Apologetics at an organization called Reasons to Believe. If you want to know more about our organization, I would invite you to visit our website, www.reasons.org, where you can learn again about uh, what we are all about at Reasons to Believe, but also you can gain access to resources that will help you explore the intersection between Christianity and science. Today we're going to take on a really provocative question, and that question is this: does the recent discovery of a protein in a meteorite provide support and validate chemical evolutionary scenarios for the origin of life? Does the recent discovery of the first ever protein isolated from a meteorite provide evidence and support for chemical evolution? This discovery was announced in early March, but because of everything happening with the COVID-19 pandemic, this very important discovery kind of got pushed to the side, became marginalized, and became kind of part of the background noise where everything that we have focused our attention on recently has been dominated by the COVID-19 pandemic. And so that means that we haven't really paid much attention to this particular discovery. But when this discovery was reported, a number of you sent me messages through Facebook, through Twitter, and other outlets asking me what did I think about this particular discovery. And so, though my response has been delayed by several weeks, again because of the COVID-19 pandemic, it's better late than never, I guess. So we're going to take on that question and more in this particular broadcast. But before we tackle the question, does the discovery of a protein in a meteorite provide evidence for chemical evolution, I'd like to ask you to do me a couple of favors. One is just take a moment if you're watching this broadcast, whether live or as a recorded broadcast, and just let me know who you are and where you're watching from. This is really valuable information as we look to plan future broadcasts, but also it's a great way for me to get to know who you are. I really want to know those of you who are watching these broadcasts. I want to get to a sense for who you are and the types of things that interest you. Also, I'd be really interested in you offering your thoughts, your perspectives on this particular scientific discovery, even if they disagree with me. My desire is that we can create a venue on my Facebook page or on our YouTube page where people can engage in civil collegial discussions about very important questions relating to the origin of life and the origin of humanity. These are questions that have profound significance that go beyond their scientific importance, but actually have implications for who we are in the cosmos. And so I really, again, want to hear your perspectives and your thoughts. And then last but not least, if you want to take a moment and ask a question or suggest a topic for a future broadcast, please feel free to do so. I read all the comments, I read all the questions, even if I don't respond to them. Your perspective, your insights are very important to me. Okay, with that housekeeping out of the way, let's go ahead and take a look at this particular discovery. And this was work reported on by a research team from Harvard University that was collaborating with scientists from the Plex Corporation and from Bruker Scientific. And what this research team was doing was looking to not only detect evidence for proteins in meteorites, but also looked to provide structural characterization of these proteins. And so this is what this work is all about. It was reported as a preprint published to a particular website that will allow scientists to publish preprints of articles that have yet to undergo a peer review process. So this article has not undergone peer review. I'm not certain if it's been submitted to a journal, and if so, which journal it's been submitted to. So this is unpublished work, technically speaking, though again the preprint has been published, and it was the preprint that generated a lot of excitement that led to a number of popular science in the news type of articles claiming that this insight uh, gives us important perspective into the origin of life process and provides some sense of validation about chemical evolution. Now, specifically, these researchers were characterizing extracts from a meteorite uh, 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 called the ACFER. I guess it's the Akfer 086 meteorite that was discovered in 1990 in Algeria. And the reason why these researchers were studying this particular meteorite is because it belongs to a meteorite class known as the carbonaceous chondrite meteorites, which are meteorites that have a high organic content to them. But this particular meteorite belongs to what's called the CV3 class. V is a particular collection of meteorites that have a characteristic geochemical signature to them. And the 3 designates the fact that this is a petrological grade 3 meteorite, meaning it's undergone very little chemical or physical alteration from the time of its formation. Now, this is really important because again, a 3 type of petrological grade means that that meteorite is giving you a perspective on the chemical and physical processes that were taking place at the time of the solar system's formation, in fact, even prior to the solar system's formation, when the material that ultimately formed our solar system still existed as a gas nebula, as a gas cloud that would then eventually condense to form our solar system. Now, the reason why these researchers wanted to study the CV3 class of meteorites is because in 2014, 2015, this research team did a theoretical study where they concluded that it was possible in the gas cloud environment in outer space, under low vacuum conditions where there's a lot of high energy radiation around, that not only could amino acids form, but those amino acids could react to form proteins, to form small proteins or to form peptides. And given the types of amino acids that would have been present in these gas clouds, they suspected that these proteins or these peptides would be hydrophobic in nature, meaning they would be water repellent, they would be insoluble in water. And they argue that while there's been a number of reports of people isolating amino acids from meteorites, there's been no reports whatsoever of proteins or peptides in meteorite samples, other than the report in 2002 by a Japanese team that claimed to have discovered evidence for diglycine, which would be a dipeptide, in a particular meteorite sample. Now, as these researchers examined the typical techniques used to extract meteorites, they realized that these extraction techniques would either hydrolyze any peptides that would have formed or would have failed to even extract them, because these typical extraction protocols involve soaking meteorite samples in water that's 100 degrees C for 24 hours. And again, they would argue that that aqueous extraction would get amino acids, but it wouldn't get hydrophobic materials. And if it did extract peptides, those conditions likely would hydrolyze them into their constituent amino acids. So therefore, they argued that a better extraction protocol would be something modeled after what's called the Fulch extraction, which is a technique that I used back in the day when I was a graduate student, but it's a system, a solvent system that is composed of a number of different individual components, including methanol, chloroform, and water, that allow you to extract materials of different hydrophobicity from samples, in this case like meteorites. And so in 2015, check that, 2017, they published a preliminary study looking at a Fulch extraction layer from the Allende meteorite, which is a meteorite that is also a CV3 class meteorite. And they concluded that they were able to, or they suspected that they were able to extract a polymer, an amino acid polymer or a protein or a peptide from this particular sample. Now, they didn't actually have direct evidence for the peptide or that protein, but rather they had a distribution of amino acids that they argued statistically would make sense if those amino acids were actually in the form of a peptide, where the analytical method that they were using to analyze the peptide would have broken it down into the amino acid constituents. And again, given the particular layer that they were analyzing from the Fulch extraction, it seemed reasonable that this would have been a hydrophobic component or material that these amino acids were constituents of. A couple of years later, they did another experiment using a highly sensitive mass spectrometry technique. It's called MALDI-TOF mass spectrometry, which stands for matrix-assisted laser desorption ionization time-of-flight mass spectrometry. It's a very high-sensitive technique that can pick up low levels of materials and is also designed to analyze high molecular weight materials like proteins. And they claimed in that study to detect a molecular fragment that was about 4,600 daltons in size, which would correspond to a protein composed of glycine and hydroxyglycine that would be about 72 amino acids in size. So this is a rather large protein fragment that they claim to have detected in this technique. In this most recent study that again was just published in preprint form, they used state-of-the-art mass spectrometry techniques, which is why they were collaborating with Plex Corporation as well as Bruker Scientific, to do a more detailed characterization of the molecular fragments, in this case from the Akfer meteorite. And not only could they do a more detailed characterization of the fragments, they were actually able to interpret those fragmentation patterns as in such a way that they could postulate the molecular structure for the protein that they had recovered from this particular meteorite sample that they labeled hemolithin. Now, what they discovered, based on the mass spectrometry analysis, was essentially two peptide chains, each about 16 amino acids in length, composed of hydroxyglycine and glycine, that then would form a duplex. And at the ends of the duplex was a really unusual iron complex, where you would have off of each of the peptide components of the duplex oxygens that would bind iron, and that iron was then bridged by 3 oxygen atoms to another iron that then would have 2 oxygens bound to it and lithium bound to each of those oxygen, where they also detected evidence for lithium associated with the hydroxyglycine residues in these peptides. Now, while the predominant species was, again, this duplex formed from 16 amino acids in each of the peptide chains for a total of 32 amino acids, the molecular weight was about 2,300 daltons, 2,400 daltons. They also claimed to detect other species that would be 15 amino acid, had chain lengths of 15 amino acids, and others that had chain lengths of 17 amino acids, as well as some lower in molecular weight species. So there's actually a distribution of these protein complexes that they found in this particular meteorite sample. Now, this is the first ever report of a protein associated with, again, a meteorite, which is in and of itself rather significant. And from a scientific perspective, this is really science at its very best. This is an impeccable piece of science. Now, in spite of that, we have to keep in mind that this, again, is not been published in a peer-reviewed scientific journal. It's been published as an unreviewed preprint, again, on a preprint service scientific website. And so it is yet to be submitted to a journal, or if it has been submitted, it is yet to undergo peer review and then been accepted for publication. So just keep that in mind. But as I look through the work and also the history of the work that this research group has done, um, I find that there's no reason to necessarily question this result. Now, having said that, Jeffrey Beta, who is a well-known origin of life researcher who has expertise in analyzing meteorite samples, questioned the reliability of the result, claiming that we have never discovered evidence for hydroxyglycine in any meteorite up to this point in time. So on that basis, he questions the result. However, this research team did actually discover evidence for hydroxyglycine in the Alande meteorite, again, a few years ago. And so while it's not true that nobody has ever discovered evidence for hydroxyglycine in other meteorite samples. Another researcher by the name of Kevin Cronin, an origin of life researcher from the UK, questions this result as well, arguing that this is a really unusual molecular species that he struggles to envision how it could ever realistically form. And I'll explain why I don't think Kevin Cronin's criticism is necessarily valid in a minute. But again, keep in mind that this has not been peer-reviewed, and there is some skepticism that's been expressed with regard to these results. We ultimately have to wait until this work is reproduced by an independent research group. But I suspect that given that the extraction protocols that have been used up to this point to analyze meteorites would have either missed or destroyed any kind of proteins that would have been present, the likelihood is that this could be a representative result that would apply to a number of different types of carbonaceous chondrite meteorites. That's not out of the realm of possibility. So then, what is the implication of this result? Well, for these researchers, they argue that this is rather significant because they claim that, again, given that they're looking at the CV3 class meteorites, that this is actually giving them a window into the time of the solar system's formation. And they would argue that there would then have been chemical processes happening during the process of solar system formation that would have generated building block materials for the origin of life, like amino acids, and even that there were pathways for these materials to undergo complexification. In fact, they argue that the deuterium enrichment that they see in this protein complex suggests that it not only is of an extraterrestrial source, indigenous to the meteorite, not Earth-based contamination, but the deuterium enrichment is so excessive that they argue that it most likely reflects the formation of this protein in the molecular cloud environment, which means that even before the solar system formed, there was prebiotic chemistry happening that could have contributed to the origin of life, meaning that when the solar system formed and early Earth formed, there would have already been an inventory of prebiotic materials available on the early Earth to kickstart an origin of life process. Moreover, they argue that the really unusual iron, oxygen, lithium complex bound to the ends of this protein could actually absorb photons, and as a result of that, use that energy to drive, for example, the hydrolysis of water molecules or other small molecules, serving as a chemical energy source that again could facilitate chemical evolutionary processes. So they argue that this work is significant because it suggests that there could have already been, again, an inventory of prebiotic materials present on the early Earth to kickstart the origin of life process, or that delivery of organic materials through meteorite mechanisms could have also built up an inventory of prebiotic materials on the early Earth, including things that were more complex than just simply the building block materials themselves. Now, as far as Kevin Cronin's criticism of this work, where he argues this is just such a bizarre molecule, I can't envision how this molecule would form in a meteorite environment or even on the early Earth, the response, I think, to that criticism would be these researchers don't think this was formed in a meteorite or on the early Earth. They think it was formed in a molecular cloud environment, where you're now looking at vacuum conditions, you're looking at these particles of solid materials that would be present that could serve as catalytic nucleation sites. You also are looking at high energy environments. And so the point being, it very well could be that even though this is a bizarre molecular species, given that we're really unfamiliar with the chemistry that can happen in the molecular cloud environment, it could very well be that this is not a bizarre, unusual species for that environment, for formation in that environment. Now, the larger question, though, is this: is this really, does this really do anything whatsoever for chemical evolution? And I question if that's the case. I think, again, this is science at its very best. I don't think the implications that these researchers are drawing from their results are necessarily unreasonable, but keep in mind that they had to rely on cutting edge, state-of-the-art analytical methods to be able to detect and characterize this material. That suggests to me that these proteins are occurring at extremely low levels in these meteorites. And that suggests to me that once they're delivered to the early Earth, there's going to be such an extensive dilution that these materials would have had no bearing on the origin of life because their concentration would have been so low as to be utterly meaningless, really being in the chemical background of the early Earth. On top of that, the reason why they were able to detect this is because they used a modified extraction protocol that, again, was designed to extract materials of a wide range of hydrophobicities. But when you look at the extraction techniques that are typically used, 100 degrees in an aqueous system over 24 hours, that would be what the meteorites would have been exposed to when they hit the early Earth. High temperature aqueous environments where it's most likely either not going to extract that material from the meteorite, therefore it's not available because it's so hydrophobic to the origin of life, or it would hydrolyze as part of the extraction process. So again, this doesn't really do much in terms of contributing to the prebiotic chemical environment of the early Earth. And let's say hypothetically it did. There's still a long pathway from having a protein that's essentially a glycine hydroxyglycine polymer to go from that to even producing more interesting biomolecules that could have contributed more significantly to the origin of life. That there's a long road to hoe going from amino acids or building block materials or even simple polymers to the very first cell, given what we understand about the inherent irreducible complexity of life in its most basic or minimal form. So I don't really see this as having much impact on the origin of life. And keep in mind, if you're looking at extraterrestrial delivery now as a potential mechanism, again, to build up the prebiotic inventory, which again, these researchers are suggesting as another implication of this work, in those delivery mechanisms not only will deliver organic materials to the early Earth, but because of the energetics involved with the impact as those materials hit the early Earth, that energy release would cause chemical destruction of those materials as well. And so that also is going to reduce the impact that these delivery mechanisms have on building up the prebiotic inventory on the early Earth. And then finally, we have actually chemical residues in rock formations that go back arguably close to 4 billion years in age, some of the very oldest minerals available to us on the early Earth. And we do see carbonaceous deposits, for example, in zircon crystals that date somewhere between 4.2 and 4.4 billion years in age. And you could argue that this could give us a window as to what did the prebiotic inventory look like on the early Earth. And we note from the isotopic distribution of these carbonaceous deposits that they don't look like they are extraterrestrial in source. We don't see a carbon-12 enrichment as we would expect. We don't see a deuterium enrichment like we would expect. But rather we see isotopic signatures that suggest that these organic materials were actually not abiotic or prebiotic in origin, but were actually biologically derived materials, indicating that life was already present on the early Earth far earlier than anybody would have indicated. So that geochemical evidence from the oldest rock formations on Earth argues against the idea that there was a high level of indigenous materials that would have contributed significantly to the prebiotic material at the time that the Earth formed, or that some kind of panspermia delivery mechanism of prebiotics to the early Earth, again, could have built up a prebiotic molecule inventory. The geochemical signatures of the oldest organic residues that we have in the oldest rocks on Earth argue against those mechanisms. So again, it's a really important piece of science, I believe. It's an incredibly elegant study that does give us some insight into what is possible in the chemical environment of molecular clouds. But to say that this has any real bearing on the origin of life, I think is probably an exaggerated claim. So anyway, I'm going to go ahead and bring the broadcast to a close and let you know that if you want to know more about why I am skeptical about chemical evolutionary scenarios for the origin of life, I would invite you to take a look at a book that I co-authored with an astronomer named Hugh Ross called Origins of Life, and then also take a look at a book I wrote called Creating Life in the Lab, where I explain why I don't think chemical evolution can account for the origin of life, and why I also think that the only way to explain the origin of life is through the handiwork of a creator, the handiwork of a mind. If you also want to check out more about the origin of life, another resource is our website, www.reasons.org. Just go to our website and type in Origins of Life, and you should find a lot of articles that can get you started in exploring this fascinating question of how did life first appear here on Earth. I'm going to go ahead and bring the broadcast to a close, just reminding you, take a moment, check in, let me know where you're watching from, who you are. Leave your thoughts, your comments on this particular scientific discovery. And then last but not least, suggest topics or ask questions for future broadcasts. Until then, I'm going to leave you with this final thought. The more that we know about science, the more that we have reasons to believe. I pray that each and every one of you stays safe, stays healthy. God bless you. Until next time.